A Pythagorean triple consists of three positive integers a, b, and c, such that a2 plus b2 equals c2. Such a triple is commonly written, and a well-known example is, if is a Pythagorean triple, then so is for any positive integer k. A primitive Pythagorean triple is one in which a, b and c are co-prime. A right triangle whose sides form a Pythagorean triple is called a Pythagorean triangle. The name is derived from the Pythagorean theorem, stating that every right triangle has side lengths satisfying the formula a2 plus b2 equals c2. Thus, Pythagorean triples describe the three integer side lengths of a right triangle. However, right triangles with non-integer sides do not form Pythagorean triples. For instance, the triangle with sides a equals b equals 1 and c equals square root 2 is right, but is not a Pythagorean triple because square root 2 is not an integer. Moreover, 1 and square root 2 do not have an integer common multiple because square root 2 is irrational. Examples: there are 16 primitive Pythagorean triples with C100. Note, for example, that is not a primitive Pythagorean triple, as it is a multiple of. Each of these low C points forms one of the more easily recognizable radiating lines in the scatter plot. Additionally, these are all the primitive Pythagorean triples with 100 less than C300. Generating a triple. Euclid's formula is a fundamental formula for generating Pythagorean triples given an arbitrary pair of positive integers m and n with m greater than n. The formula states that the integers form a Pythagorean triple. The triple generated by Euclid's formula is primitive if and only if m and n are coprime and m minus n is odd. If both m and n are odd, then a, b, and c will be even, and so the triple will not be primitive. However, dividing a, b, and c by 2 will yield a primitive triple if m and n are coprime. Every primitive triple arises from a unique pair of coprime numbers m, n, one of which is even. It follows that there are infinitely many primitive Pythagorean triples. This relationship of a, b and c to m and n from Euclid's formula is referenced throughout the rest of this article. Despite generating all primitive triples, Euclid's formula does not produce all triples, for example, cannot be generated using integer m and n. This can be remedied by inserting an additional parameter k to the formula. The following will generate all Pythagorean triples uniquely, where m, n, and k are positive integers with m greater than n, m minus n odd, and with m and n coprime. That these formulas generate Pythagorean triples can be verified by expanding a2 plus b2 using elementary algebra and verifying that the result coincides with c2. Since every Pythagorean triple can be divided through by some integer k to obtain a primitive triple, every triple can be generated uniquely by using the formula with m and n to generate its primitive counterpart and then multiplying through by k as in the last equation. Many formulas for generating triples with particular properties have been developed since the time of Euclid. Proof of Euclid's formula. That satisfaction of Euclid's formula by a, b, c is sufficient for the triangle to be Pythagorean is apparent from the fact that for positive integers m and n, m greater than n, the a, b, and c given by the formula are all positive integers, and from the fact that a simple proof of the necessity that a, b, c be expressed by Euclid's formula for any primitive Pythagorean triple is as follows. All such triples can be written as where a2 plus b2 equals c2 and a, b, c are coprime, and where b and c have opposite parities. From we obtain and hence, then, since is rational, we set it equal to in lowest terms. We also observe that equals the reciprocal of and hence equals the reciprocal of, and thus equals. Then solving for and gives since and are fully reduced by assumption. The numerators can be equated and the denominators can be equated if and only if the right side of each equation is fully reduced, given the previous specification that is fully reduced. implying that m and n are co-prime. The right sides are fully reduced if and only if m and n have opposite parity, so that the numerators are not divisible by 2. So, equating numerators and equating denominators, we have Euclid's formula with m and n co-prime and of opposite parities. A longer but more commonplace proof is given in Moyer and Sierpinski. Interpretation of parameters in Euclid's formula. Suppose the sides of a Pythagorean triangle are and suppose the angle between the leg and the hypotenuse is denoted as then an. Elementary properties of primitive Pythagorean triples. General properties. The properties of a primitive Pythagorean triple with a less than b less than c include is always a perfect square. This is particularly useful in checking if a given triple of numbers is a Pythagorean triple, but it is only a necessary condition, not a sufficient one. The triple 6, 12, 18 passes the test that 2 is a perfect square, but it is not a Pythagorean triple. When a triple of numbers a, b and c forms a primitive Pythagorean triple, then and 1/2 are both perfect squares. However, this is not a sufficient condition, as the triple 1, 8, 9 is a counterexample, since 12 plus 82 92. At most one of a, b, c is a square. The area of a Pythagorean triangle cannot be the square or twice the square of a natural number. Exactly one of a, b is odd, c is odd. Exactly one of a, b is divisible by 3. Exactly one of a, b is divisible by 4. Exactly one of a, b, c is divisible by 5. The largest number that always divides a, b, c is 60. All prime factors of c are primes of the form 4n plus 1. Therefore c is of the form 4n plus 1. The area is an even congruent number. In every Pythagorean triple, the radius of the incircle and the radii of the 3x circles are natural numbers. Specifically, for a primitive triple the radius of the incircle is r equals n, and the radii of the x circles opposite the sides m2 n2 to Minnesota, and the hypotenuse m2 plus n2 are respectively m, n, and m. As for any right triangle, the converse of Thaler's theorem says that the diameter of the circumcircle equals the hypotenuse. Hence for primitive triples the circumdiameter is m2 plus n2, and the circumradius is half of this and thus is rational but non-integer. When the area of a Pythagorean triangle is multiplied by the curvatures of its incircle and 3x circles, the result is 4 positive integers w greater than x greater than y greater than z, respectively. Integers w, x, y, z satisfy Descartes' circle equation. Equivalently, the radius of the outer Soddy circle of any right triangle is equal to its semi-perimeter. The outer Soddy center is located at D, where ACBD is a rectangle, ACB the right triangle and AB its hypotenuse. There are no Pythagorean triples in which the hypotenuse and one leg are the legs of another Pythagorean triple. This is one of the equivalent forms of Fermat's right triangle theorem. Each primitive Pythagorean triangle has a ratio of area to squared semi-perimeter that is unique to itself and is given by no primitive Pythagorean triangle has an integer altitude from the hypotenuse. That is, every primitive Pythagorean triangle is indecomposable. The set of all primitive Pythagorean triples forms a rooted ternary tree in a natural way. See Tree of primitive Pythagorean triples. Special cases. In addition, special Pythagorean triples with certain additional properties can be guaranteed to exist. Every integer greater than 2 that is not congruent to 2 mod 4 is part of a primitive Pythagorean triple. Every integer greater than 2 is part of a primitive or non-primitive Pythagorean triple. For example, the integers 6, 10, 14, and 18 are not part of primitive triples, but are part of the non-primitive triples, and There exist infinitely many Pythagorean triples in which the hypotenuse and the longer of the two legs differ by exactly 1. One method to generate such triples is the relation 2 plus 2n, 2 equals 2n plus 1, 2, leading to triples, etc. More generally, for every odd integer j, there exist infinitely many primitive Pythagorean triples in which the hypotenuse and the even leg differ by j2. There exist infinitely many primitive Pythagorean triples in which the hypotenuse and the longer of the two legs differ by exactly 2. Generalization. For every integer k greater than 0, there exist infinitely many primitive Pythagorean triples in which the hypotenuse and the odd leg differ by 2k2. There exist infinitely many Pythagorean triples in which the two legs differ by exactly 1. For example, 202 plus 212 equals 292. For each natural number n, there exist n Pythagorean triples with different hypotenuses and the same area. For each natural number n, there exist at least n different Pythagorean triples with the same leg a, where a is some natural number. For each natural number n, there exist at least n different Pythagorean triples with the same hypotenuse. There exist infinitely many Pythagorean triples with square numbers for both the hypotenuse c and the sum of the legs a plus b. According to Fermat, the smallest such triple has size A equals 4,565,486,027,761, B equals 1,061,652,293,520, and C equals 4,687,298,610,289. Here A plus B equals 2,372, 1592 and C equals 2,165, 172. This is generated by Euclid's formula with parameter values m equals 2,150,905 and n equals 246,792. There exist non-primitive Pythagorean triangles with integer altitude from the hypotenuse. Such Pythagorean triangles are known as decomposable since they can be split along this altitude into two separate and smaller Pythagorean triangles. Geometry of Euclid's formula. Points on a unit circle. Euclid's formulae for a Pythagorean triple can be understood in terms of the geometry of rational number points on the unit circle. To motivate this, consider a right triangle with legs A and B, and hypotenuse C, where A, B, and C are positive integers. By the Pythagorean theorem, A2 plus B2 equals C2, or, dividing both sides by C2, geometrically, the point in the Cartesian plane with coordinates is on the unit circle x2 plus y2 equals 1. In this equation, the coordinates x and y are given by rational numbers. Conversely, any point on the unit circle whose coordinates x, y are rational numbers gives rise to a primitive Pythagorean triple. Indeed, write x and y as fractions in lowest terms, where the greatest common divisor of a, b, and c is 1. Then, since x and y are on the unit circle, as claimed, tangent half-angle formula, there is a 1-to-1 correspondence between the rational numbers in and the primitive Pythagorean triples. The tangent half-angle formula for the angle alpha opposite the side of length of a Pythagorean triangle gives, which will be a rational number. In particular, if 0 less than a less than b, then tan will be a rational number in the interval. The process has an inverse. Whenever tan is a rational number pq, the formulas sin equals 2 tan equals 2 pq, and cos equals give the Pythagorean triple equals with the less than b. It will be a primitive Pythagorean triple when p and q are relatively prime, unless p and q are both odd, in which case equals 2 will be a primitive Pythagorean triple. Stereographic approach. There is therefore a correspondence between points on the unit circle with rational coordinates and primitive Pythagorean triples. At this point, Euclid's formulae can be derived either by methods of trigonometry or equivalently by using the stereographic projection. For the stereographic approach, suppose that P is a point on the x-axis with rational coordinates. Then it can be shown by basic algebra that the point P has coordinates. This establishes that each rational point of the x-axis goes over to a rational point of the unit circle. The converse, that every rational point of the unit circle comes from such a point of the x-axis, follows by applying the inverse stereographic projection. Suppose that P is a point of the unit circle with x and y rational numbers. Then the point P, obtained by stereographic projection onto the x-axis, has coordinates which is rational. In terms of algebraic geometry, the algebraic variety of rational points on the unit circle is birational to the affine line over the rational numbers. The unit circle is thus called a rational curve, and it is this fact which enables an explicit parameterization of the points on it by means of rational functions. Pythagorean triangles in a 2D lattice. A 2D lattice is a regular array of isolated points where if any one point is chosen as the Cartesian origin, then all the other points are at where x and y range over all positive and negative integers. Any Pythagorean triangle with triple can be drawn within a 2D lattice with vertices at coordinates, and the count of lattice points lying strictly within the bounds of the triangle is given by for primitive Pythagorean triples. This interior lattice count is the area equals the first occurrence of two primitive Pythagorean triples sharing the same area occurs with triangles with sides and common area 210. The first occurrence of two primitive Pythagorean triples sharing the same interior lattice count occurs with and interior lattice count 2,287,674,594. Three primitive Pythagorean triples have been found sharing the same area, with area 13,123,110. As yet, no set of three primitive Pythagorean triples have been found sharing the same interior lattice count. Spinors and the modular group. Pythagorean triples can likewise be encoded into a matrix of the form A. Matrix of this form is symmetric. Furthermore, the determinant of x is which is 0 precisely when is a Pythagorean triple. If x corresponds to a Pythagorean triple, then as a matrix it must have rank 1. Since x is symmetric, it follows from a result in linear algebra that there is a column vector Xi equals Mn T such that the outer product holds, where the T denotes the matrix transpose. The vector Xi is called a spinor. In abstract terms, the Euclid formula means that each primitive Pythagorean triple can be written as the outer product with itself of a spinor with integer entries, as in the modular group gamma is the set of 2 times 2 matrices with integer entries with determinant equal to 1. Alpha delta minus beta gamma equals 1. This set forms a group, since the inverse of a matrix in gamma is again in gamma, as is the product of 2 matrices in gamma. The modular group acts on the collection of all integer spinors. Furthermore, the group is transitive on the collection of integer spinors with relatively prime entries. For if Mn T has relatively prime entries, then where U and V are selected so that mu plus Nevada equals 1. By acting on the spinor Xi, the action of gamma goes over to an action on Pythagorean triples, provided one allows for triples with possibly negative components. Thus if A is a matrix in gamma, then gives rise to an action on the matrix X in. This does not give a well-defined action on primitive triples, since it may take a primitive triple to an unprimitive one. It is convenient at this point to call a triple standard if C greater than 0 and either a relatively prime or a relatively prime with the 2 odd. If the spinor Mn T has relatively prime entries, then the associated triple determined by is a standard triple. It follows that the action of the modular group is transitive on the set of standard triples. Alternatively, restrict attention to those values of m and n for which m is odd and n is even. Let the subgroup gamma of gamma be the kernel of the group homomorphism where SL is the special linear group over the finite field Z2 of integers modulo 2. Then gamma is the group of unimodular transformations which preserve the parity of each entry. Thus, if the first entry of Xi is odd and the second entry is even, then the same is true of A Xi for all A gamma. In fact, under the action, the group gamma acts transitively on the collection of primitive Pythagorean triples. The group gamma is the free group whose generators are the matrices. Consequently, every primitive Pythagorean triple can be obtained in a unique way as a product of copies of the matrices U and L. Parent-child relationships. By a result of Berggren, all primitive Pythagorean triples can be generated from the triangle by using the three linear transformations T1, T2, T3 below, where A, B, C are sides of a triple. If one begins with 3, 4, 5, then all other primitive triples will eventually be produced. In other words, every primitive triple will be a parent to 3 additional primitive triples. Starting from the initial node with A equals 3, B equals 4, and C equals 5, the next generation of triples is the linear transformations T1, T2, and T3 have a geometric interpretation in the language of quadratic forms. They are closely related to reflections generating the orthogonal group of x2 plus y2 minus z2 over the integers. A different set of three linear transformations is discussed in Pythagorean triples by use of matrices and linear transformations. For further discussion of parent-child relationships in triples, see Pythagorean triple.